Today we are going to discuss a very important problem of classical physics or waves and oscillation. This is actually the problem of linear harmonic oscillator. Actually, the problem of linear harmonic oscillator, which is also called a spring mass system, is a key problem of classical physics. You will find the solution of this problem by various tools in classical physics. But here our discussion is very elementary based on the concept of simple harmonic motion. So you can see this figure. Actually in this figure I have shown there is a massless spring. Actually first of all we are considering a massless spring, but you will see in the last part of the lecture we will consider a massive string. But first of all we are considering that this spring shown in this figure is massless and its spring constant is K. One of the ends of this spring has been attached to a wall, as you can see in this figure at this point A, and the another free end is attached to a block which is placed on a smooth surface, that is a frictionless surface. Okay. Now you know when the spring is neither stretched nor compressed, that is the spring is its natural length, then no restoring force or no spring force is developed. Okay. In this condition, the block is at the point O and the forces acting on the block you can see in this free body diagram. The force of gravity mg acting on the block is acting in vertically downward direction, and the normal force due to the surface is in vertically upward direction. Actually in this condition you can see the block will be in equilibrium because the net force mg minus n will be equal to 0. So this point O is the equilibrium position of the block. Now let us consider from this equilibrium position the block is displaced by x, so that according to this figure the spring will get stretched. On the other hand, you can also compress the spring. So you can say that this x is either the elongation or the compression in the spring. Actually when the spring will get stretched or compressed by x, then a restoring force will develop, as I have shown in this second free body diagram. Here mg and n are the forces at each, but a force F, which is actually of restoring nature, this force is developed due to the elastic property of the spring, and this tends to bring the block towards the equilibrium position O. Actually in general this restoring force, which we can write Rf, this is a non-linear function of the displacement x. It is given by kx minus ax square plus bx cube and so on. Okay, this is the general form. As in this condition you can see that this restoring force is a non-linear function of x. So if the block will be released, it will oscillate about the equilibrium position, but that oscillation will be not simple harmonic, because for simple harmonic motion you have studied that this restoring force must be a linear function of x. So if we consider the limiting condition of a small oscillation, that is if you consider that this displacement x is very small, then what will happen? If x is very small, all the terms containing the higher powers of x, that is x square, x cube, that will be negligibly small, and in that condition this restoring force, which I am now writing F, this will be equal to minus kx. Why I have written this minus sign? You know, since this force is of restoring nature and it always tends to decrease the value of x, so indicating this sense of restoring force I have put here minus sign. And as in this condition f will vary linearly with x, so if you will release the block, this restoring force will bring the block to the equilibrium position, and due to inertia this will shoot out from the equilibrium position and the spring will get compressed. Then a spring pushed the block. So in this way, under this restoring force, the block will perform simple harmonic motion about its equilibrium position O. And from this result, you can easily see what will be the time period, what will be the frequency of oscillation. All these things I have mentioned here for your convenience. As you can see, when the spring is neither stretched nor compressed, then net force is 0 and the equilibrium position is O. But if the block is displaced, then restoring force is given like this, as I have mentioned. Okay, so you can say that the restoring force varies non-linearly, and this variation of the restoring force I have shown in this graph. Okay, and as I have told you that in the limiting condition of a small displacement, this restoring force will be given by minus kx, because all the terms containing higher power of x will be negligible. And as you know, when f is directly proportional to minus x, motion is simple harmonic. So this block will execute SHM about its equilibrium position O. And as you have learnt earlier, that if the motion is simple harmonic, then what is the time period? The standard formula for time period is given by t equal to 2 pi root over m by k. So knowing the value of k and m, you can easily find the time period. Okay. Now, one of the part of the problem that if you have to show that the motion of this spring mass system will be simple harmonic, you can easily prove this only writing this expression for the restoring force. Okay, and you can also get the expression for time period, because this is the standard result for the time period of a oscillator executing simple harmonic motion. Okay, you can easily show. But now let us try to find the equation of motion of this oscillator. As you can see, we have obtained that f is equal to minus kx, but according to Newton's second law of motion, what will be this resultant force F? According to Newton's second law of motion, you know F is the product of F is equal to product of mass and acceleration. Since x is the displacement at time t, so acceleration will be d2x by dt square. So instead of f, you can write m times d2x by dt square, and that will be equal to minus kx. And so you can write d2x by dt square is minus k by m times x, and this k by m is replaced by omega square. So the equation of motion of this oscillator becomes d2x by dt square plus omega square x equal to 0. You can remember this equation is nothing, this is the standard equation of simple harmonic motion. So it is obvious that under the condition of a small displacement or under the limiting condition of a small oscillation, the motion of this spring mass system is just a simple harmonic motion. Okay, and you know this omega, which has been written for a square root of k by m, this is cyclic frequency of the oscillation, and omega you know is equal to 2 pi over t, where t is the time period, and so 2 pi over t is equal to a square root of k by m, and hence you can get t is equal to this much. This is the standard formula for the time period of a spring mass system. So this spring mass system is also called a spring pendulum. So I have written in the title a spring pendulum. Now you can see this time period t of this spring mass system or spring pendulum is independent of g. It does not depend on the acceleration due to gravity, as I have mentioned it here. As you have seen earlier that the time period of a simple pendulum depends on g. So at different places, when a simple pendulum is brought, its time period varies. But if you will bring this spring pendulum at different places on the surface of the earth, or if you will bring it at different planets or different satellites where G will change, but the time period of a simple pendulum will not change. This is a very remarkable fact. If a question is asked that if you uh, take a simple pendulum and a spring pendulum in a satellite and the satellite revolves, the time period of the simple pendulum will be what? Since time period of a simple pendulum, you know this is given by 2 pi root over Lg. And when the satellite revolves, it is in the state of free fall, so G will become 0 and time period of a simple pendulum then becomes infinite. It means that the simple pendulum will stop oscillating. But a spring pendulum, the time period of a spring pendulum will remain unaffected. On the other hand, you can see that time period of a simple pendulum given by this formula 2 pi root over L by G is independent of mass. But time period of a spring pendulum depends on mass. As you have seen that this T is a square proportional to a square root of m. Okay, and it also depends on K, and K, you know, this is called force constant, and force constant is an elastic property of the spring, so it depends on the elastic property of the spring. Okay, now this was a very simple fact, very simple calculation, but this concept is very useful in solving the numerical problem, particularly for competitive examination. So I would now like to discuss all the important facts so that you can solve any numerical problem or objective type of question or subjective question based on this spring mass system. Now, a question is invariably asked that if there are two blocks, you can see in this figure, of masses m1 and m2, and they are attached by a massless spring of a spring constant k. Then if you will actually compress this two masses so that the spring will get compressed, or if you will stretch the spring and release the masses, what will happen? Actually, this is a two-body problem because the spring has been connected to two finite masses. And you know, in classical mechanics, there is very simple technique to solve such a problem. This two-body problem can be reduced to a single body problem, okay, by the concept of reduced mass. Actually, you can imagine that this spring is attached to a single mass having mass mu. You can see this second figure. And the another end of the spring is attached to an infinite mass that is by a wall. When you say wall, that means infinite mass. Okay? And if mu is the reduced mass of this system, then this two-body problem is equivalent to this one-body problem. And what will be this mu? You know, if mu is the reduced mass, then 1 by mu is equal to 1 over m1 plus 1 over m2. So you can thought that there is no two masses attached to the spring, but there is only one mass having mass mu, and that mu is given by this formula. And then you think that there is only one mass mu attached to this spring. And then what will be the time period? You can say that this time period will be equal to 2 pi root over m by k, and at the place of m we will write mu. Okay, we will write mu, and mu will be found by this relation. From here you can see that this mu will be equal to what? This will be m1 times m2 divided by m1 plus m2. So in this way, a two-body problem can be easily solved. Although I will solve this problem in next video independently by writing the equation of motion. But here I have just provided you a very simple technique. Whenever there will be a question like this, you have to reduce the two-body problem into a single body problem by replacing the two masses by its equivalent reduced mass. And then you should think that there is only one mass attached to the spring, and so the time period will be like this, and mu will be substituted from here. Okay, so I think you have definitely understand. Such a question is invariably asked in civil services examination. You can see the particularly I have seen in IFS examination, Indian Forest Service, a question was asked that there is a molecule of HCl, H plus and Cl minus, which is just like a dipole, and when when its dipole moment changes, that is length between distance between H plus and Cl minus will change, it will oscillate, and what will be the time period. Here at the place of M1 you have to write mass of hydrogen ion, and at the place of M2 you have to write mass of chlorine ion, and you can get the time period. Okay, so you can solve such a problem. I have actually explained this here, you can see. Okay, so this was a very important fact. Now another important problems which are asked related to this spring mass system are when there is two or more springs connected to one another. Actually, there will be three types of problems: springs in series, springs in parallel, and mixed springs in mixed combination. I have actually discussed here the parallel combination and series combination of a spring, and that can be used when the spring will be in mixed combination. Okay, let us see here in first figure that I have considered two springs having a spring constant K1 and K2. Okay, and a block of mass M is connected to them. Now if this block will be displaced from its equilibrium position and released, again this block will perform a simple harmonic motion if the displacement is small. So what will be the time period in this condition? How we can find it? Actually, this two springs connected in series can be assumed to be equivalent to a single spring, as I have shown in this second figure, and the spring constant of this equivalent spring I have considered there, this is Ks. S subscript has been used for the word series. Okay, so if you find the value of Ks, what will be the value of Ks, then you can easily find what will be the time period. Now let us consider that this mass is displaced in this direction by x, so that the spring K1 is elongated by x1 and K2, the second spring is elongated by x2. Let us consider. So I have assumed here that x1 is extension or compression of spring 1 and x2 is extension or compression of spring 2. As these two are connected in series, you can see the figure. So the total displacement of this block is, if x, then definitely this x will be equal to x1 plus x2. Okay, it is obvious. Now x is the equivalent displacement, and since springs are massless, so the tension in a spring, that is the spring force, a spring force is tension developed in the spring, and you know if the springs are massless, then tension throughout this system will be same. So the spring force developed in the first spring will be also F, and that of in second spring will be also F. Okay, and the spring force developed in this equivalent spring we will also assume F. And as you know that F is equal to minus Kx. Okay. So X will be what? This is minus F by K. So instead of X, we will write minus F by Kx. Instead of X1, we will write minus F by K1. And for X2, we will write minus F by K2. Since in all terms there will be minus sign, so that minus will cancel out. So I have not written here minus. So you can write F by Ks equal to F by K1 plus F by K2. Now F will cancel out and you can see 1 over Ks will be equal to 1 over K1 plus 1 over K2. So if two springs of spring constants K1 and K2 are connected in series, the equivalent spring constant will be, if Ks, then 1 by Ks is equal to 1 over K1 plus 1 over K2. Or you can say that this Ks is equal to K1 times K2 over K1 plus K2. You can see this result is same as capacitors in parallel. Capacitors in parallel. Definitely you have studied when two capacitors of capacitance, say C1 and C2, are connected in series, then the equivalent capacitance CS is given by 1 over C1 plus 1 over C2. So the springs connected in series is just equivalent to capacitors connected in series. Okay. But this result is just opposite to the resistances connected in series. Okay. In general, if there will be n springs connected in series, you can generalize this result. You can see I have written in general, if there are n springs connected in series, all are massless, then 1 over Ks will be equal to 1 over K1 plus 1 over K2 plus so on plus 1 over Kn. Now once you know the equivalent spring constant, then you can think that there are not two springs, but there is only one spring having a spring constant Ks, and that is connected to this mass M. Then this problem is just a spring mass system, and you can easily write the time period. Time period will is 2 pi root over M by K. Here at the place of K we will write Ks, and this Ks will be substituted from here, and you can easily get the time period. Okay, I think we have clearly understand this idea. Now let us see the case of springs in parallel connection. When one of the ends of all the springs are connected to the wall and the other ends connected to the same block, then the springs are said to be in parallel. Okay. As you can see in this first figure, I have shown there are two massless springs of a spring constant K1 and K2, and they are connected in parallel, and a block is of mass M is connected to them. Actually, this second figure is just equivalent to the first figure. In this second figure, the two springs are also in parallel. Don't be confused that these are in series. Why? As you can see in first figure, one of the ends of the two springs are connected to this mass. Here you can also see the one end of a spring 1 and one end of a spring 2 are connected to the same mass, and the other ends to wall. So here the other end of the first spring is connected to a wall, and the second spring is also connected to a wall. So there is no difference between this first figure and the second figure. Both are same. Okay. Now in this case, how we will find the equivalent spring constant? Okay. So let us consider that this block is displaced by x. As you can see, when this block will be displaced by x, each spring will get stressed by x. Or if the block is compressed by x, each spring will compressed by x. So in this case, x are same. In series combination, f is same, and in parallel combination, x is same. But forces will be different. Why? Because The spring constants are different. So in first spring, the restoring force developed will be F1 equal to minus K1x, and that in the second spring, the spring force will be minus K2 times x. Okay, minus K2 times x. Okay, both forces are actually in same direction. So if you want to draw the equivalent figure for this connection, how you can draw it? Let us consider there is a spring constant Kp equivalent to this combination connected to the same mass m. Then if this mass will be displaced by x, the same force F will be developed in the spring, and this mass will perform SHM. So in this case, you can see that the resultant force F, that will be actually equal to what? The net force acting on this block will be the sum of F1 and F2, because both F1 and F2 are acting in same direction. So in this case, you can say that F is equal to F1 plus F2. But for the getting the value of F, you can see this equivalent figure. Third figure is the equivalent figure of the combination, and this F will be equal to minus Kp into x. Kp, P has been used for parallel combination, and F1 will be minus K1x, F2 minus K2x. Again, each term will contain minus sign, so I have omitted that. So I have written Kp times x equal to K1x plus K2x. Now x is a common factor that will cancel out, and so you will get the equivalent spring constant Kp, that is equal to K1 plus K2. And this is just equivalent to the parallel combination of capacitors. This is parallel combination of capacitors. Result is same. Okay. And once you get the value of equivalent spring constant, then using the formula for time period, which is 2 pi root over m by k, you can get the time period of this system. At the place of k, now we will write Kp, and the value of Kp will be substituted by simply adding the spring constant of each spring. Okay. So I think you have clearly understand it. Whenever there will be a problem having the mixed combination of a spring, you should use this idea to simplify the problem. Okay. Now, till now we have considered the case of a spring mass system when a spring has been assumed massless. But you know, in practice there will be no spring which will have no mass. Definitely there will be some mass in the spring. So now we are going to consider the spring mass system having massive spring. So you can see this figure. In this figure I have again shown that there is a spring of length L, and it is attached to a mass m, and the another end of the spring is again attached to a wall, and the block has been placed on a smooth surface, horizontal surface. Okay, and the spring constant is K. And this spring has a mass, let us say ms. Ms is the mass of the spring. Now in this case too, if this block is slightly displaced from its equilibrium position and released, then again it will perform simple harmonic motion. And if you have to show that its motion is simple harmonic, you have to obtain its equation of motion. But in this case, writing the expression for a force and applying Newton's second law of motion for getting the equation of motion, the problem will be very tedious. Actually, this problem is easily solved by using the energy concept. As you know, in case of a spring mass system, the force acting on the block is a spring force, which is a conservative force, and you know that when a body moves under a conservative force, its total energy remains conserved, constant. So if we will obtain what is the total energy of this spring mass system at a given time t, and that energy will be constant. Using the idea of conservation of energy, you can easily find what will be, you can easily prove that motion of this spring mass system is simple harmonic. You can obtain the equation of motion by the energy consideration. Okay. So now let us try to obtain the total energy of this spring mass system when this mass has been displaced by x, but x is very small. We are talking about the limiting condition of a small oscillation. Okay. Actually, when this block will be displaced by x and released, then you know this block will be acted upon by the spring force and it will move toward the equilibrium position. Let us consider that when displacement is x at time t, then this mass m acquires a velocity v. Okay, so this mass will have kinetic energy. As a spring is not on in its natural length now, so a spring force is developed, and so the spring will have elastic potential energy. But apart from that, since a spring is massive, so a spring will also have kinetic energy. So here actually there will be three types of energy: kinetic energy of this block, kinetic energy of a spring, and the elastic potential energy of the spring. Okay. We can obtain the expression for all these three energies, and then after adding you will get the total energy of this system. Okay. So let us see this calculation. You can see I have considered that ms is mass of the spring and L is its natural length. Okay. The total energy of this system at any time t when the block is displaced by x, if it is E, then E will be equal to US plus KS plus KM. Here US represents the elastic potential energy of the spring, KS represents the kinetic energy of the spring, and KM kinetic energy of the block. Okay. Now you can see what will be the values of these three energies. US, this is elastic potential energy of the spring. As the spring has been elongated or compressed by x, so you know the elastic potential of energy of a spring is half kx square. This is a well-known formula. And when the block is released, you have assumed that its velocity is v, which is given by dx by dt. So at that moment, the kinetic energy of the block km will be half mv square, and at the place of v you can write dx by dt. So you can say that its kinetic energy is half dx by dt whole square. Okay. Now let us try to find what will be the kinetic energy of this spring. You cannot write the expression for kinetic energy of the spring directly. Why you cannot write? Because you can see, if you can see this figure, this end at A of the spring is connected to a wall, which is just a rigid support. And so velocity of the spring at this end A is always equal to 0. Okay. And this another end of the spring, let us say at B, is connected to mass m, and mass m has acquired velocity v. So velocity of the other end of this spring is v. It means velocity of the spring is not constant throughout, but it increases from 0 to v. Have you understand or not? Velocity of different section of this spring will be different. So in this case, if you will write the expression for kinetic energy by the formula half ms v square, what will be this v? You cannot say, because v is not constant. It varies from 0 to v. Okay. So for calculating the kinetic energy of this massive spring, let us consider a very small element of this spring between these two sections P and Q. I have considered that from the fixed end the distance of this element is S and the length of this element is ds. This is a small increment of S. So if this element is so small that its velocity will have a unique value, and if you are able to calculate the kinetic energy of this element, then after integrating that value you can get the kinetic energy of the whole spring. Okay, so let us first of all try to find the kinetic energy of this element. How we can find it? For this you have to find the mass of the element. As you know, a spring has a length L and mass of length L is ms. Okay, so mass of unit length of the spring will be what? This will be ms by L. Okay, and length of this element is ds. So what will be the mass of length ds of this spring? This will be ms divided by L into ds. This is actually the mass of this element. So I have written here mass of the element PQ, which is dms, that is equal to ms divided by L into ds. Okay, have you understand or not? Definitely you have understand. Now let us try to find what will be the velocity of this element. How we can find it? As you know, at this end B, which is at a distance L from the fixed end, the velocity is v. So at end L, velocity is v. So at unit length, what will be the velocity? This will be v by L. And since this element is at a distance s, actually in comparison to s you can neglect ds. So at a distance s, velocity will be what? This will be s by L into v. But you know v is what? V is equal to dx by dt. So you can see that velocity of this element will be equal to s over L into dx by dt. I have written it here. Velocity of the element is this much. Have you understand or not? Definitely you have understand. Okay, very good. Now you know the mass of the element and you know the velocity of the element. So you can write the kinetic energy of the element dks, and that will be 1 over 2 mass of the element. This is ms over L into ds. You can see it here. And v square, v means velocity of the element. This is s over L times dx by dt whole square. Okay, this is the kinetic energy of this element PQ. Now integrating this result, we will get actually the total kinetic energy of the spring. So let us integrate it. So kinetic energy of the spring Ks is equal to integral 1 over 2 ms by L ds times s over L dx by dt whole square. Here integration is with respect to this s, and you know s varies from 0 to L. Here s is equal to 0 at the fixed end, and at this another end where mass has been attached, where there s is equal to L. So the limits of integration will be 0 to L. So except this s and ds, every terms are constant. So Ks will be equal to what? This will be ms over 2L cube times dx by dt whole square integral 0 to L s square ds. Okay, and this integral will be L cube by 3. So now this L cube and this L cube will cancel out, and so you can see the kinetic energy of a spring is 1 over 6 ms times dx by dt whole square. Okay, in this way we have calculated the kinetic energy of the spring. Now you can get what will be the total energy. As you can see, total energy is the sum of these three energies, and the values of these three energies I have just written here. This is US, this is Km, and you have obtained Ks. So substituting all these three values there, you can see that total energy will be equal to 1 over 2 m plus ms by 3 times dx by dt whole square plus half kx square. This is the total energy of this spring mass system at time t. Okay, this is a function of time. Okay. Now, as I have told you that since the block is here oscillating under the elastic force of a spring, which is a conservative force, so this spring mass system is a conservative system, and you know the total energy of a conservative system is constant. So you can say that E is equal to constant, and if E is constant, dE by dt is equal to 0. So now let us differentiate the total energy E defined in this equation 5 and equate that to 0. You can see what will be the differential coefficient. Since 1 over 2m plus ms by 3, this is a constant factor, and we have to differentiate this dx by dt whole square. This is just a function of function. So what will be this? This will be 2 times dx by dt into d2x by dt square. Okay? And now the derivative of second term, half k is constant, and when x square will be differentiated with respect to t, this is also function of function. What will be that? That will be 2x times dx by dt, and that is equal to 0. Now you can see this 2 and this 2 will cancel out. This 2 and this 2 will also cancel out. Okay? And this dx by dt is a common factor, and dx by dt is not 0. So remove this dx by dt. After removing it, you get this is m plus ms by 3 times d2x by dt square plus kx equal to 0. Now if you will take this m plus ms by 3 as a common factor, or if you divide the LHS of this equation by this factor m plus ms by 3, what will be your result? Your result will be d2x by dt square plus k over m plus ms by 3 times x equal to 0. Now, you can compare this result with the standard equation of the spring mass system. You have seen that the equation of motion of a spring mass system is d2x by dt square plus k over m into x equal to 0. And at the place of this m, what is here? At the place of m, you can see this is m plus ms by 3. So this massive spring mass system can be assumed like this. You can thought this problem by this technique. If you consider that your spring is not massive, but it is massless, okay? But at the place of m, you consider that there is a mass connected by a mass having value m plus ms by 3. It means in this case we consider the effective value of mass. If you consider that a spring has no mass, it is massless, but the effective mass of this system is m plus ms by 3. Then this problem is just equivalent to the spring mass system having massless spring. Okay, so at the place of m, we will write m plus ms by 3, and comparing this equation 5 with the standard equation of simple harmonic motion, you can see that as the standard equation is d2x by dt square plus omega square x barabar 0. Here at the place of omega square there is k by m plus ms by 3. So omega is equal to this much, and you know time period is 2 pi over omega. So the time period of this spring mass system is equal to 2 pi times square root of m plus ms by 3 over k. Actually, this is the actual result. This is the general result. Now, if you consider that in comparison to m, this m is much greater than ms. It means mass of a spring is much smaller than the mass of block, or you say that mass of a spring is 0. Then your result for time period will be 2 pi root over m by k, which we have just obtained earlier independently. So actually, when you talk about the spring mass system, definitely there will be some mass in the spring, and so this equation 6 is the general result. And from this result, you can easily obtain that if a spring is massless or a spring has a negligible mass in comparison to the mass of the block, then the time period will be 2 pi root over m by k. I think definitely you have clearly understand this problem. Okay. Now, lastly, we are going to see that if the spring is if the block is not on the horizontal surface, but it is suspended from the massless spring, then what will happen? Actually, this is the case of a spring pendulum, just like a spring pendulum. So see this first figure. We have again considered that this spring has a natural length L, and we have suspended a block of mass m, okay, to this spring. As you know, due to the force of gravity or due to the weight of this spring, this block, this spring will get stretched. So let us consider that this spring is stretched by x naught. So the total length of the spring will become L plus x naught. And then this block is in equilibrium. So you can say that this x naught is the elongation of the spring in equilibrium state. Okay. So as the block is in equilibrium, so net force on it will be 0. What are the forces acting on the block in this condition? One force is force of gravity acting in downward direction. And since the spring in equilibrium condition is stretched by x naught, so the spring force developed will be kx naught. Okay. So the net force as the block is in equilibrium will be 0. So mg minus kx naught is equal to 0, or you can say that kx naught is equal to mg and x naught is mg by k. This is the equilibrium elongation of the spring. Now, if from this equilibrium position, if this block is displaced in downward direction from the equilibrium position, or it is moved up, anything can be done. Then what will happen? Let us consider that from this equilibrium position, which I have marked by this dotted line, the spring is further, the block is further depressed by x and released. What will happen? Now, you can see the total length of this spring will be now what? This will be L plus x naught plus x. It means now this spring is elongated by x plus x naught. X plus x naught. So the spring force developed in this condition will be what? That will be k times x plus x naught, which is acting in upward direction. Okay. And mg, as earlier, it is acting in downward direction. So in this condition, there will be a net force acting on this block in upward direction, and that net force will be equal to kx. How? As you can see, the resultant force can be given by mg minus k times x plus x naught. Okay, and this can be written as mg minus kx minus kx naught. But you have seen that this mg is equal to kx naught. So this will cancel out and f will be equal to minus kx. So you can see, again we get the same result. I have not calculated the equation of motion further because you have seen all these things earlier. So since f is again proportional to minus x, It means the restoring force varies linearly with the displacement x, so the motion will be simple harmonic motion and time period will be same, that is t equal to 2 pi root over m by k. Okay, so in this condition actually this block will oscillate about this equilibrium position, let us say O. Okay, when you will release it from this displaced position, it will move up, and at this position again the net force will be 0, but due to inertia this will move up, but when it is above this equilibrium position, then a spring force will act in downward direction, and after becoming its velocity 0, the block will return back, and in this way under this restoring force exerted by the spring, the block will oscillate simple harmonically about this equilibrium position. So I think this complete idea of a spring mass system is clear to you, and watch the video seriously. This is just something long video, but as our aim was to clear all the concepts regarding this problem, so I have made some longer video. So don't be worried, watch it with patience and definitely you will get benefited. Thank you very much.